Welcome back to the 6th video in our Random Forest series. In this video, we'll look at how random forest can be used to estimate and impute missing values in test samples. In the previous video, we discussed how to estimate and impute missing values in training samples. If the test samples also contain missing values, the procedure is slightly different. For training samples, we can use the target labels when obtaining the initial estimates because the labels are known. After that, we train the random forest, construct the proximity matrix, and use it to update the initial estimates and obtain more accurate values. For test samples, however, we do not have target labels, and we cannot use the samples to train the model. In this video, we'll see how missing values in test samples can be estimated and imputed. Let's say we have the following training and test datasets. Let's say we have 4 training samples and 1 test sample. The test sample contains 1 missing value. This example is adapted from the StatQuest video. Although the training samples originally contained missing values as well, let's assume that all of them have already been imputed using the procedure we discussed in the previous video. As a result, the training dataset is now complete and contains no missing values. Let's also assume that a random forest model has already been trained using the training samples. The first step is to assign an initial estimate to the missing value in the test sample. For training samples, we can use the target labels when obtaining the initial estimates because they are known. For test samples, however, the target label is usually unknown because it is what we want to predict. Therefore, we cannot use target labels when obtaining the initial estimate. Instead, for numerical features, we use the overall mean or median of that feature across all training samples. In this example, the overall mean of the training samples is 172.0. So we use that value as the initial estimate for the missing value in the test sample. Next, we pass both the training samples and the test sample through the trained random forest model. We then create a leaf node assignment table like the one shown here. The rows correspond to the training and test samples, and the columns correspond to the trees in the random forest. Let's assume that the forest contains 5 trees. Each cell shows the leaf node assignment for a sample in a particular tree. For example, both the first training sample and the test sample fall into leaf node 1 of tree 1. Now, just as we did in the previous video, we use this table to construct the following proximity matrix. The only difference is that this time the test sample is included in the matrix as well. As a result, the proximity matrix contains similarity information for all 5 samples. After normalization, the last row and the last column contain the similarity weights associated with the test sample. Since we normalize the matrix column by column, we use the last column as the weight vector. These weights indicate how similar the test sample is to each training sample. The similarity between training sample 1 and the test sample is 0.36, which is relatively high. This is because 2 of their feature values are identical. The same is true for training sample 4 and the test sample. Once we have the proximity matrix, the remaining steps are the same as those used to estimate missing values in the training samples. For numerical features, we compute a similarity-weighted average using the proximity weights. Now let's estimate the missing value in the fourth feature, weight, of the test sample. The feature vector for weight, including the test sample, is shown here. Next, we multiply this vector by the proximity matrix. This produces a new vector of length 5. This vector contains the new estimates for the weight feature. Since we're estimating the missing value for the test sample, we're only interested in the fifth element of this vector. Therefore, we update the initial estimate of 172.0 with the fifth element of the new vector, which is 161.3. When estimating missing values in the training samples, we repeatedly retrain the random forest, construct a new proximity matrix, and update the estimates. For test samples, however, we do not repeat this process. This is because test samples cannot be used for training. Therefore, the updated value of 161.3 becomes the final estimate. Next, let's estimate a missing value in a categorical feature of the test sample. In this example, the test sample contains one missing categorical value. This example is also adapted from the StatQuest video mentioned earlier. The first step is to assign an initial estimate to the missing value. Since test samples do not have target labels, we typically use the most frequent category among all training samples as the initial estimate. In this example, no is the most frequent category, so we use it as the initial estimate for the third feature of the test sample. Next, we update this initial estimate. There are two possible approaches. The first approach uses the proximity matrix. This is the same method we used in the previous video to estimate missing categorical values in the training samples. For each category, we simply sum the similarity weights in the fifth row of the proximity matrix. Only sample 2 has the value yes, so the total weight for yes is 0.09. Samples 1, 3, and 4 have the value no, so the total weight for no is 0.36 plus 0.18 plus 0.36, which equals 0.9. Since the total weight for no is larger than the total weight for yes, we update the missing value to no. For training samples, we repeatedly retrain the random forest, construct a new proximity matrix, and update the estimates. For test samples, however, the update is performed only once. Again, this is because test samples cannot be used for training. The second approach does not use the proximity matrix. Instead, it relies only on the trained random forest model. We create multiple copies of the test sample, one for each possible target label, and then estimate the missing value for each copy separately. In this example, the target label can be either yes or no. So we create two copies of the test sample. For the first copy, we assume that the target label is yes. For the second copy, we assume that the target label is no. We then evaluate which assumption is more reasonable. Let's start with the first copy. We look at all training samples whose target label is yes. Among those samples, we find the most common category for the feature containing the missing value. In this example, there is only one such sample, and its category is yes. Therefore, we temporarily fill the missing feature with yes. Next, we pass this completed sample through the trained random forest. Let's assume that the forest contains 5 trees. Suppose 4 trees predict no and only 1 tree predicts yes. This means that only one of the 5 trees supports our assumption. The probability supporting this assumption is therefore 1/5, or 20%. The remaining 4 trees disagree with our assumption. Now let's repeat the same procedure for the second copy. We look at the training samples whose target label is no. Among those samples, we find the most common category for the feature containing the missing value. In this example, the most common category is no. Therefore, we temporarily fill the missing feature with no. We then pass this completed sample through the trained random forest. Suppose 4 trees predict no and only 1 tree predicts yes. This means that 4 out of the 5 trees support our assumption. The probability supporting this assumption is therefore 4/5, or 80%. Under the assumption that the target label is no, the sample appears much more consistent with the training samples. Therefore, it is reasonable to use the imputed feature value obtained under this assumption. As a result, we estimate both the missing feature value and the target label itself as no. One particularly interesting aspect of this approach is that the imputation process and the prediction process are tightly integrated. While filling in the missing feature, we simultaneously evaluate the possible target labels. As a result, missing value imputation becomes part of the prediction process itself. This idea is briefly mentioned in the original Random Forest webpage by Leo Breiman and Adele Cutler, which we introduced in the first video of this series. Now let's compare these two approaches. The first approach requires constructing a new proximity matrix whenever the test sample changes, so it can be computationally expensive. However, it takes the similarity between samples into account and is generally more accurate. The second approach relies only on the trained model and does not require a proximity matrix. As a result, it is much faster. Even when the test sample changes, missing values and target labels can be estimated quickly. The two approaches do not always produce the same result. If the results differ, the estimate obtained from the first approach is generally considered more accurate. In these two videos, we've explored how random forest proximity matrices can be used to estimate missing values in both training and test samples. In the next video, we'll move from theory to implementation and write Python code that builds the entire procedure step by step.